Hello, everybody. We will start in 1 minute. We still see people joining, so let's give them 1 more minute and we'll start. Okay, let's start. So, first of all, welcome everybody to our fourth webinar of the amazing series Advanced Hardware Hacking and its Countermeasures. Today, we are going to discuss the fault injection attacks on modern embedded devices such as FPGAs, microprocessors, microcontrollers. Before we start, let me introduce the speakers of this webinar. So my name is Oren Hollander. I'm an embedded architect expert in the fields of ASIC, FPGA, ARM, and security, hacking and defending. Together with Lionel from Ishar, the security analyst, we deliver all of these webinars together, theory, news, and practical demos to give you not just to see the news, but also that the tools supporting them and what can be done by yourself or your companies. So our agenda for today is the following. We'll first describe the recent fault injection attacks on the embedded devices. Then we'll split the solutions into two countermeasures implemented by the silicon vendors, what you get on the device from hardware perspective. And then what else need to be done either by the silicon vendor libraries or by yourself, which is the software-based fault injection protection, how to write, let's say, secure code that will make these attacks more less easier. Yeah. And then we will show the 2026 fault injection attacks and mitigation techniques, the most modern one or the latest one. And at the end, we'll have a demo on laser fault injection to show you how it's actually done, what is the reverse engineering required, and all the steps. Let's start. By the way, if you have any questions, please type them in the chat box so we will be able to address them at the end of the meeting, either immediately or by email. Yeah. So let's start. So I decided to start first of all to put all the audience in the same context. So historically, we know that fault injection was what we call rich man's game. That means someone required $100K laser stations and some localized clean rooms, very expensive. However, between 2020 to 2026, this changed due to two factors. The first one is the democratization, and the second one is automation. So regarding democratization, a project like Pico EMP, which is based on a $4 Raspberry Pi Pico, and another example, the Chip Whisperer platform, those low-cost hardware moved fault injection into the hands even of hobbyists or students. More importantly, the use today of RL, reinforcement learning, also solved the parameter search problem. So instead of humans spending weeks or months finding the exact nanosecond to glitch a chip, an AI-driven script can now help to test thousands of voltage timing combinations per second, finding the exact glitch window automatically. Later, you will see what are we talking about glitch window when Lionel will show you how to find the exact glitch window with laser. The idea is that this moved the threat model for devices from low risk to critically vulnerable. And this is, as you will see, it's also part of the standard FIPS 140-3. So it's important thing to understand. Let's take a look on attack vectors. We know that the voltage fault injection, what we call VFI, works by momentarily with dropping the supply voltage, the VCC, of a processor or FPGA or microcontroller just below its operational threshold. The idea is that the effect of that is this induces a propagation delay fault, or in simple terms, the electrical signal doesn't reach its destination before the next clock cycle begins. We can skip instructions. On modern ARM Cortex-M, like M33, M55, M85, if you time this glitch during a compare instruction, for example, the logic gate responsible for setting the zero flag may fail to switch. That means the CPU then reads success state even if the signature, for example, check failed. Okay. In 2024, we saw an interesting rise of a new attack here that called multi-voltage glitching, MVFI. And the idea here is that the attacker pulls two different power rails, for example, the core VCC plus the IO rail, in a specific sequence. This allows the attackers to bypass double checks in software, which is one of the countermeasures that we'll see later, by glitching the first check and then the second check 500 nanosecond later. The second thing that we see is that we know that electromagnetic fault injection, EMFI, uses a small copper coil to induce localized electrical current inside the silicon without touching it. So it's like non-invasive technique. This is like a ninja attack because it bypasses the physical shields that only detect contact or light. However, the most terrifying modern vector is remote fault injection, specifically the PM fault attack. Yeah, in the past, it was assumed that to create a fault injection, you must have the hardware in your hands, physical access. And some companies said, oh, there's no way to access my system physically. But here, the remote fault injection attack is a new attack vector that you need to be aware of. Let me give you an example. Modern server motherboards, like those from Supermicro, use what we call the BMC, baseboard management controller, to monitor health of the system. This BMC has access to something interesting that we call the PM bus. This is the power management bus, which tells the voltage regulators on the device how much power to send to the Xeon, for example, processor. That means that if an attacker gains root access to the BMC, for example, via software exploit that he found, they can command the regulator to glitch the CPU voltage, which allows a remote attacker to break Intel SGX or ARM Trust Zone security enclaves from across the world. Okay, so he doesn't have to have the hardware in his hands, and this means that it's effectively turning a software vulnerability into hardware physical attack. This is interesting combination of those two fields. Okay, now to see the modern fault injection techniques before we will look at the countermeasure, I would like first of all to say that this picture is not accurate. The probes, for example, here are not the right one, but let's talk about the different techniques themselves. So let's start with the BBI, the body biasing injection. This is the idea here is to apply a high voltage pulse to the backside of the silicon, what we call substrate. The idea is that it is more localized than EMFI, but it's cheaper than laser fault injection. Attacker use it to target the wafer level chip scale packages where the die is inherently exposed. The second one that you will see later, a demo, let me change it to laser for a second. Yeah, here, the multidimensional LFI. This requires an advanced laser setups, but it uses multiple synchronous beams to bypass redundant logic. For example, dual core lockstep that you have in many CPUs, microcontrollers that related to safety in automotive or other fields. The idea is that by faulting both the primary and the redundant logic simultaneously, the attacker can defeat traditional hardware duplication that we'll see later. Next, we have the AI, which is something that emerged, assisted parameter searching. Again, because we know that AI emerge, it takes some time to have a reliable solution, but it's still on the way. The idea is that attackers now use the reinforcement learning to automatically discover the glitch window, as I mentioned before, the nanosecond scale timing needed for a successful fault. The idea is this just reducing the time to break device sometimes from weeks to hours. And then we have the remote software, remote PM fault, for example, what we mentioned before with the BMC. And last but not least is something that I would like you to be aware is something new called RAM jam. So people who are familiar with external memory attacks like DDR, they may be familiar with row hammer and jackhammer. This is another technique emerged 2025, just last year, that exploit the dual port RAM in FPGAs. The idea is by concurrently writing opposite values to the same memory cell over and over, the attackers create transient short circuits that induce faults in neighboring logic. So it's something that need to be monitored by companies who build the highly security systems today. Okay, to put something in context, all of these slides tells, yeah, you can be attacked here and there. The question is, are there really devices in the field that hacked with these techniques? So I gathered here several examples. We will not talk on all of them, but I will give you some ideas. So for example, let's start. We have here microcontrollers, microprocessors, and FPGAs. Let's start with the NXP LPC 55S69. I'm very familiar with this device because it's part of our training and on security for embedded systems. So here the Trazon M was bypassed. Let me emphasize that the physics of the chip is now today in the new software vulnerability. Researchers broke NXP device, microcontroller, a chip marked for its security, by the way. There's a lot of very nice features inside. They use the multi-voltage glitch technique that I described before. It demonstrates how multiple glitches can bypass instruction level countermeasures and trust zone boundaries. So the idea is that voltage fault injection is no longer about crushing the device or the chip. It's about instruction flipping. Okay, so you can imagine that what's actually happened is that on this device, a precise glitch during the image verification stage, the authentication stage, doesn't corrupt the image itself. It's corrupt the program counter. And by that, this wild jungle jump sends the CPU to a memory address of the attacker choosing, where he can run his payload. Uh, Tesla, also very interesting stuff. Cars. A lot of people like to hack Elon Musk things, the Starlink, the Tesla, anything. And in this case, researchers demonstrated the 2023 37C3 conference that the glitching, by glitching the AMD secure processor, the ASP, on the autopilot board on the car, they could gain root shell access. So they didn't actually crack the encryption, they glitched the stage one bootloader to believe the signature was valid. This allowed them to extract private user data and enable full self-driving features that were behind a paywall. For FPGA, I believe that many of you are familiar with the Starbleed attack discovered 2020 on Xilinx 7 series FPGA, AMD FPGAs. Vulnerability in the configuration engine actually allows an attacker to use the FPGA as decryption oracle. What does it mean? By repeatedly glitching the configuration reset while reading back the bitstream, the device actually leaks its own decrypted secrets. And because this was implemented in hardware, it's not patchable. And you can find information also on AMD website, and on the internet, of course. Same thing for another Xilinx FPGA, the UltraScale Plus, which is even newer. There was a found vulnerable to just start attack, which uses fuzzing to find undocumented commands in the hardware state machine that bypass effectively the RSA authentication entirely. This, by the way, proves that as long as there is a hardware state machine, there's many times a path to bypass it via timing and logic faults. And that's important thing to know. Then we are going to talk now about countermeasures that are implemented in the latest devices. We'll take some examples. But before that, I would like first to emphasize the difference between the software level countermeasures and the hardware level countermeasures. So basically, the software level countermeasures are relatively easy to implement and are generic. You'll see that in a few minutes. But you need to understand that software level countermeasures alone are not enough, especially since we are dealing with implementation attacks. Hardware level countermeasures, on the other hand, are more powerful, but of course complex to implement. Unfortunately, implementation attacks cannot be fully prevented, but only mitigated by reducing the leakage or increasing the difficulty of the attack. You need to take into account also the fact that countermeasures have limitation and constraints, of course, and it depends on the specific project. For example, physical limitation, the device may have limited space, heat dissipation, weight capacity that restrict the choice of the countermeasures. Performance. Countermeasures may affect the speed, power consumption, or even reliability of the device or the algorithm. Cost. The countermeasures, of course, may increase the engineering effort. Sometimes you need to add extra components. The integration become more complex, the testing time, etc., etc. And of course, time to market. The countermeasures may delay the launch of the product or make it even less competitive in the market. So, first of all, let's start to see what are the countermeasures that implemented by silicon vendors. Because there are many new devices that popping up every week, I decided to take as a use case two devices, one FPGA and one microprocessor. Here I chose Altera Agilex 5, the latest FPGA from this company, and i.MX95, also a very new CPU from NXP. When I made a comparison between them, because recently I made a comparison between Agilex and Versal from AMD for the security features. Here I compared those two devices, and what I found is that there is a difference or divergence in security philosophy between these two companies. NXP focuses, for example, on highly isolated standalone secure enclave that you see here called EdgeLock, that will tell you about it in a few minutes, while Altera emphasizes redundancy and monitoring via a centralized manager. Both devices, by the way, are designed to meet the requirements of FIPS 140-3. The NXP support even level 4, Agilex 5 up to level 3 of the standard. And the idea behind FIPS 140-3 is that this latest standard introduces stricter requirements for physical security and non-invasive attack like fault injection mitigation. That means the world consider fault injection and side channel attack very seriously because of the success in the market of these attacks. So just a few words, the NXP i.MX95, and again, just the use case, use the EdgeLock secure enclave. This is just for your intention, kind of an autonomous subsystem with its own CPU, RAM, ROM. It's physically separated from the main Cortex-A55 cores that you can find on the device. It contains as well on-chip glitch detectors that monitor the VCC line for any transient drop faster than, for example, 5 nanoseconds. If a glitch is detected, if you ask yourself, the enclave locks the cryptographic ports preventing the leaked data from reaching the rest of the SOC. Intel Agilex used the SDM, Secure Device Manager, inside the device. This has, as you can see here, triple modular redundancy, 3 CPUs. And that means the SDM logic is duplicated 3 times. If a fault injection, for example, flips a bit in one core, the other 2 cores outvote it, and security fault is raised. It also have interesting feature called internal scrubbing, which constantly scans the configuration memory for bit flips caused either by electromagnetic fault injection or natural radiation. For example, if it's go to space, like um, satellites and things like that. This is just an example. So that means the silicon vendors do things inside the devices to make them more robust against fault injection. So software hardening best practices. Now we go into what else can be done by the designers. So I wrote here 3 interesting practices that are very recommended in this field, and we'll see in a few minutes some examples in C code. First of all, it's important to understand that to defend in software, we must assume first of all that the hardware is unstable. Okay? So temporal redundancy means that we perform the critical checks twice, separated by random delay like jitter. Double negative logic, as you can see, instead of writing if authorized in our condition, which is just a 1-bit Boolean that can be 1 or 0 and easily can be uh, affected by fault injection, we will use a longer value. Here it's 16 bits. So to glitch this, an attacker must flip 16 specific bits. No, it's 32 bits. But they are just different. I mean, they are duplicated inside. And to glitch this, an attacker must flip, as you can see, 16 specific bits. Whereas a simple fault injection just need to flip 1 bit. So of course it's much more challenging. And step counters, the idea here, for example, if we take a look on a secure boot sequence, we would like to increment a progress variable, let's call it like that, at each stage. So before jumping to the kernel or to other function, we verify that the counter is exactly the expected value. This prevents instruction skipping from jumping directly to the final stage, like what fault injection like to do, bypassing if, else, while loop, etc. Let's take a look on a few examples. The first one is branch redundancy. The threat that we are fearing here is that we know that glitching relies on injecting single fault, and therefore we would like to reduce the number of single points of failures. How we do that? We would like to check a value, then check the value again, and then branch only if both check passed. So in this example, we validate that the encryption of a password, um, happens as it should be, executing decrypting of the result. Yeah. Uh, and the purpose of the email string compare, of course, is to prevent the attacker from using the same fault twice. So if the result match, we return the encrypted password. Otherwise, we fail silently because we don't want to provide to the attacker any extra information. If someone asks himself what is the reason that in the first if I compare it to 0 and on the next one I compare it to the opposite condition, it's not by mistake. We know that the purpose here is to prevent the compiler from introducing an optimization and reuse the result of the first string compare, and therefore remove the second string compare from the image. Some compilers, by the way, some compile optimizations are smart enough to detect this redundancy. Therefore, is usually recommended to disable compiler optimization for this segment of code. The next thing is checkpoints. So we would like to check that all paths were executed, which is a very important thing against fault injection. The recipe that we are going to use here is that for each branch, we would like to track and update a variable x, for example, in this case, the variable called checkpoint. Then we'll check the variable x against pre-computed value. And if it fails, we know that our control flow was altered. So the code pattern that you see here validates that our program successfully executed all parts of the code it was supposed to execute. This is performed by using a variable, as you can see, to track the execution of the code and comparing it to pre-computation computed value. That's important. And the last thing is, on this slide is the three-state decisions. We know that many times the attacker will try to glitch after you do some reverse engineering if-else checks because it's true or false. It's just usually one bit. In C, by the way, if statements, in C, if statements, any non-zero value represent true. So the strategy we would like to do, instead of using the code on the left-hand side, which is easy to be glitched, we would like to define or use, if you like, a non-trivial value to present false, non-trivial value to present true, and all other values will represent false. The values representing true and false should not differ by a single bit. Otherwise, they can be also fault injected by one bit. So the idea is that so we know that with fault injection, it is possible to corrupt any non-zero value. Therefore, we can result in a successful fault. That's why we actually have three options in the code. You see, we have if, else if, and else. And this is how we now the attacker can still defeat this defense if you do a good reverse engineering by using a technique called register spraying. He can actually try to inject values to specific registers before this function or something called, and then the value will be there. So in order to prevent that, what we would like to have is that the SIG-OK will always use a return value that is dynamically generated, okay, and not a constant. Another technique we have is called instruction cycle counting. This is very useful for secure boot, for example. You would like to make sure that all steps in the secure boot were actually executed. So what we would like to do here is just to count the number of instruction cycle an operation should take and compare it to a non-execution time. That means if you design the product, you know, you wrote the code, you have everything, you have a white box, you can measure how long each function actually takes, embedded that in the code, and then test it. And if something happened too quick, you know that something skipped probably, or there's some timing violation. So the recipe here is that we would like to first start the counter. Yeah. Then we perform the operation that needs to be monitored, for example, hash and of course RSA, whatever. Then at some point stop the instruction counter, and then validate the counter value and the supposed value. By the way, it's important to maybe mention that this method is effective during atomic operation, where no risk of interrupt or task switching. If you would like to deal with task switching, schedulers, and interrupts, you need to add other techniques as well. So yeah, the next one is the last one here that I'm going to show today is the walk backwards. Again, the idea is that the hacker would like to skip some if else and continue in the code. What we do here, we actually do the steps backwards. So if something is skipped, the idea is that the result will be totally invalid code flow and something that can be easily detected. So what we'd like to do is to force odd jump operation in the source code. We need to turn off the compiler optimizations because that could actually take out all of our efforts. And we need to perform confirmation of the resulting assembly code using this assembler. last two things before I give the things to Lionel. I would like to first summarize the 2026 fault injection attack and mitigation because these are the, let's say, modern techniques today. On top of what everybody knows, it doesn't mean that the previous one, previous attack doesn't work anymore. They still do. So let's for AI-driven glitch search, we talked about it. It's make the finding the glitch window much faster. The difference to make this to beat this technique is by implementing what we call random jitter and clock randomization. With that technique, we ensure that the execution time of sensitive function like a signature check varies by a few microseconds every time it runs. The attacker AI model can never converge on a successful trigger point, something that Lionel will talk about later, the trigger point. You're effectively making the search space actually mathematically infinite for the attacker, even if you use AI. Uh, the remote PM bus undervolting and the solution here is very simple. Use authentication and encryption of the traffic. Yeah, because historically it was not. Laser fault injection, something that Lionel is going to show you. The mitigation against that is a better active top layer metal mesh shields with a good accuracy. This is now standard, by the way, in high security SOC like the IDOTM X95 that I showed before. This is a thin energized web of metal covering the sensitive parts of the die. So if laser tries to penetrate it, or if a probe tries to mill it away, the circuit is broken. Yeah, so the hardware recognizes this as a fatal tamper event and immediately zeroes eyes or wipes your encryption keys before the attacker can even begin their glitching sequence. Um, for instruction skipping, the idea is to have hardware-assisted control flow integrity. This is something that we see that is already built in our V9 and modern RISC-V architectures. The idea is that the hardware maintains a shadow map of where the program is allowed to go. In ARM, we call that realms. If a glitch caused the CPU to jump to an unauthorized memory address or skip a branch, for example, the hardware detects a control flow violation and then halts the system instantly. That means you are moving the security logic from the vulnerable software into the hardware silicon pipeline. And last but not least, which everybody talk about it also these days, post-quantum key cracking, something that Ishad had last month webinar on that. The idea here is that we know that traditional RSA and ECC are becoming obsolete. However, simply switching to post-quantum cryptography is not enough because the PQC algorithms like MDSA are mathematically complex and highly sensitive to fault injection during the signing process. So to fix it, you need to stick to the NIST PQC standards implemented within Secure Enclave. That means would like to run these algorithms in a complete isolated environment like NXP Edgelog that I showed before or Intel Secure Device Manager. The idea is that we would like to protect the mathematical operation from being glitched. We are not just protecting against the quantum computers of tomorrow, we are actually protecting the algorithms themselves from the hardware hackers of today. And last but not least, I add here kind of something that you can take away with you. What are the questions that you need to ask yourself as a project leaders or people at the team if you are actually protected against fault injection? I split it into several fields. We have here the hardware part, software part, and testing part. So just to take an example, hardware root of trust, you need to ask yourself, does the device use as an isolated secure enclave like edgelock? Is it compliant to FIPS, to standard? Is it have active meshes, etc., etc.? What detectors are there? For example, uh, are there any software countermeasures that were added? And also how things were actually tested. For example, automated glitch fuzzing, the question that you need to ask yourself, has the device undergone automated parameter searching for its glitch window? Is it easy to use AI tool to find it and hack the device? Remote fault injection simulation, the idea here, can the system, for example, withstand a 10% voltage drop on its core rail for 20 nanoseconds without leaking register contents? Has ever anyone tested that, checked that, or just say, yeah, I'm protected? And by that, I will give the hands to Lionel. So let me stop my sharing.
Yes, okay. Thank you, Oren. I think everyone can see my screen now. Yeah. Okay, so hi everyone. I will go for this demo into a use case which is based on a system on chip, here the IMX8. But before starting, just a small highlight. Here I'm going to go through an example, but people often ask, okay, what is the best method to perform fault injection, etc. Sadly, the answer that people really does not like is it depends. So you will need to think about what is the asset you want to protect, on what it will be operated. Do you have security mechanisms implemented at the hardware level, the software level, or in your implementation, just like Orange showed to you before. So it will require testings. And again, according to what you want to do with this device, do you want to go for a certification, evaluation, or you want to be very strong on the field for a very long period of time? It will depend on your use case. So that being said, let's jump right in. Here, I will go through this IMX8 use case where we'll perform laser fault injection. I could have chosen other techniques, of course, could be voltage or power glitch, EMFI, body bias fault injection, but I will focus on laser fault injection for different reasons, especially the precision that will be required for search targets, as we will see its characteristics. So this is the bench that I used, and I need more than this laser station. Lots of other things, so oscilloscopes, motorized stage, the power, so the laser source as well, delay generator, fault reset, because so to allow turning on and off the device, because during a fault injection campaign, the device will crash. Okay, so on this IMX8 system on chip, what do I have? I do have a non-protected AES 128, so full software implementation. I also have a hardware-assisted implementation of the AES 128. So basically, in the ARMv8 instruction sets, you do have hardware-assisted part of the encryption that you can use to go faster. And there is also a crypto processor which provide a secured AES 128. So these are the possibilities that we can play with on these targets, and I will choose the ARMv8 assisted one. So let's see, now that I know what I want to work on, what strategy can I put in place? So again, 3 different targets. I decide I want to attack the ARMv8 target, so I will need to start somewhere. This is the picture that I have obtained with a laser fault injection setup, doing some scanning and X and Y with the optical focus of the objective, did this cartography and took several pictures and reassembled them all together. Of course, as I'm going to do laser, my DUT needs to be prepared. So that could also be first challenge. In some cases, it's not even possible. You also need the flip chip so that the silicon is directly visible to the IR camera, but also for the laser faults, the laser beam, basically. So once we have that, we cannot grasp basically if it's big or not, but once we have that, we will need to state, okay, where do I start? Where is my AES going on? So you will need to search for that in multiple dimensions, so space, as we can see here, but also in time. When is it starting from the moment I send some comments for encryption, for instance? So this is why we need to determine a methodology, how to work on such a topic. So we'll go through the TUT characteristics, so what I can know from the documentation or public or non-public documentation, then playing with the device itself, seeing how it's made, what I can do, what I can learn, and then go for the fault injection experiment. All right. So let's go for the characteristics on this IMX8. So this is an 14 nanometers FinFET technology, which is quite small. But as you might know, today, 7 nanometers, 5 nanometers, 2 nanometers are even on the field. So a bit more challenging for, let's say, locating the interesting areas and especially faulting them. So this one is 14 nanometers. It's a system on chip with 4 Cortex A53. So another challenge. Where is my AES going to take place? Okay. And this one is also quite fast related to classical microcontrollers. It can run up to 1.8 gigahertz. So these can start to explain why I chose this laser system for that, because I will need precision in space and I will need precision in time. So the laser systems are the most accurate for that. The laser systems could also be completely overkill in other scenarios. So this is why I come back to what I said at the beginning. It depends on your targets. It depends on what you want to do. So in order to work on this DUT, I will have all the software environment to set up. And usually, if I have control on the DUT, which is the case in this example, I will start to characterize how this DUT will react to some fault injection stimuli. For instance, if I try directly to work on the AES, I have low chance to find the area where it happens when I expose it to fault injection. If, for instance, I do very, very similar and basic codes that just run a loop of doing nothing or writing the same value into memory, and I inject a fault, I will more easily find the set of parameters that will make, or at least would have some effect on the chip. So this is why we often start with characterization with basic test codes. Once these basic test codes have revealed some good fault injection parameters, we will then jump to the actual targets. And again, I recall you, I will use the ARMv8 AES instruction. So for the rest, of course, we need to communicate with the DUT. So now I know what I want to target, and I will need to get some information out of the chip. So here, before doing fault injection, we rely on side channel analysis. So for multiple reasons, here we have done, before working with lasers again, a side channel cartography. So we took this cartography information and we just overlay it on top of the chip, just to locate where the activity is taking place. With this information, we can determine where we will do the fault injection analysis. It reduces quite greatly, if you look at the size of the chip, it greatly reduces the area to cover and save a huge amount of time. There are more advanced techniques to more clearly locate where you have such activities, such as the photonic emission analysis, which will very, very precisely eventually count photon emitted very locally on the chip. But here, let's just use the classical side channel analysis, and we have this. And with this chip prepared, the picture I had before, you will need, if you need to reconstruct such images, some process to create this background. Because if you are the manufacturer, you have the blueprint, you have the layout, no problem. If you are not the manufacturer, it's not very likely that you will find it on the online or on public sites. So you need to do it yourself. So for that, yet another problem, imaging or having a good high resolution imaging of your chip so that you can work on and eventually identify more closely the infrastructure or the architecture or the structure that you would have on the chip that would be related to the operation of interest. So once you have that, you can also switch to the other big dimension that will matter is time. So you will need to know when to inject the faults. Before that, you will need to know when your AES is starting, how long it will last, if you have jitter, if you have, all those things related to timing we need to be tackled before doing the fault injection campaign. So here in this example, we again rely on sidechain to characterize the timing of our fault injection campaign. The goal being to have a very stable reference in time from which I would be able to inject delays with a delay generator to target specific rounds or even specific clock cycles. Okay, so and it can be kind of complex. If you look at this picture here, where we have the AES encryption, so this one is from the crypto processor, you will see that the signal is very, very faint and not super easy to read. It's already averaged here without jitter. So imagine adding jitter and randomness in that. That will be a nightmare to work with. And that's the reality of today. So in order to tackle those, I would say, synchronization issue, you can rely on different techniques based on the GPIO if it's not too slow regarding the targets, or pattern detection, smart pattern detection for these kind of targets. So here we can locate basically the moment when the AES starts, when it ends. My goal would be from this AES that I want to attack to perform a DFA, so differential fault attacks. So if I use the Piret and Quizquater technique, I will need to focus towards the end, so the last 2 rounds in which I want to tamper with the encryption. So I can reduce also the time frame during which I will do the fault injection. So from my starting reference points, I will then compute, for instance, the fixed delay from which the interesting part of my encryption will start. And then it will be from these points, trigger fixed delay plus small delays to target clock cycles eventually, that I will play my fault injection campaign. It is really, really important to reduce as much as possible the space to cover and the time frame to cover as well, again, to save time, because there are lots of other parameters that we will need to cover. Okay, so I have this information from this analysis, and I will start playing with my laser system. So in this example, I have a simple laser system with the IR camera, XYZ stage. I do have the laser source, which is a PDM here, my DUT. I need the scope to monitor everything, the OptiSpot to being able to focus the laser view independently from the Z axis. It means that I can keep optical focus, so see where I am and the structure in the logic, and in the same time move independently the focus level of the laser beam, okay, which will allow me to go more or less deep in the silicon. So with this laser bench, you have also multiple options. Magnification factor for the lens. So the higher magnification factor, the smaller spot size. Again, I can go down with the 50x, which is not listed here, down to 1 micrometer spot size on top of the die. It's great for precision, but it's also way more possibility to cover in terms of space. So again, we need to handle in a clever manner the fault injection parameter search. Usually, what we'll start with is maybe with a 20x, some bigger spot size, and with coarser grain approach, trying to eventually find some areas that will respond. And then in a second iteration, for instance, refine those parameters to get more precision. Okay, so there will be multiple iteration. And this is where AI-driven fault injection parameter search could help to optimize or go faster to some good subset of fault injection parameters. So this will be the experiment. So I will, I think, move faster to the next one. And basically, this notebook is the one that I've copied for the real experiments, and I've adapted a bit so that I can just execute it here with you, but without being connected to the actual laser system. So I will need to communicate with my DUT. Okay, then I will need to start communicating with my laser bench system. On this laser bench system, I might have some cameras like the overview camera inside the enclosure, which of course in this virtual example does not exactly correspond to that. I will have my infrared camera. So with the infrared camera here, you will have the sights that allows you to spot the middle of the camera view, which is not necessarily the location where the laser spot will shoot. So you can recenter the laser spot, or if you have double laser fault injection system, you would be able to move these spots inside the view of the field of view of the lens. Okay, so you have these options here so that I can see what is going on during my experiments. Then I will instantiate also my OptiSpots. So again, this motor that will set basically the focus level of my laser beam. I will need also to move things around. So for that, I will rely on the motorized stage. So X, Y, Z, so X, Y, Z axis. And I will be able to basically move around and select areas. Of course, at the beginning, I might use this manually to go to some interesting locations. And then when I will need to automate the campaign, I will script this stage. Here I have a few values that I've taken from the previous experiments. So basically the reference points that I will need to use. Next, I will instantiate my PDM, so my laser pulse, my laser source. Here, I would be able to basically set the current set points. I will use peak current and not continuous current here. But the question here is, which is the correct value? At the beginning, you don't know. So it's an exploratory phase. So you can start with very low set points. If sometimes you start too high, you have also some chances to just kill the device. So again, it requires attention and tests with very small step, particularly for the power handling. Okay. Another timing question is, how long should I activate the pulse? How long will it last? And that again will depend. What are you targeting? Are you targeting a single clock cycle? So you know the frequency, you can do the division by yourself and count the amount of time this round will last, and you will just set the value here accordingly, okay? Or maybe you want to target multiple cycles because your operation of interest lasts multiple cycles. Or on the contrary, you are trying to target on a pipelined architecture with, let's say, fetch, decode, execute steps, just one of these steps within one cycle. So you can also basically change the pulse width this way. Again, at the beginning, maybe you don't know. So you will need to select some frame, a time frame for the pulse duration. Okay. And of course, the duration of the pulse, like the exposure time when you take a photo, for instance, will also have an impact on the amount of energy that you will inject on the chip. So that needs to be taken into account as well. So once you have your laser source, you will need to handle the timings of the delays related to the external trigger that we have found thanks to side channel. So here, again, you will simply be able to specify what is the delay from the moment you receive the trigger and how long the pulse will also last. Okay, so once I have all those equipments, this is where I can start working on my cartography. So I will take the picture that I've built with this reconstruction imaging technique. I will set some reference point here, and then I will be able to select the area. Remember, this is a quad core cortex. Here I do have the quad core. So core 0 might be core 1 here, core 2. So the indexes are not correct, but it might be something like this with the interconnect between the two. Which one is the right one? I don't know. So at the beginning, when I did the experiment, I scanned everything. Turns out after the experiments, my code were only triggering core 0 because I was working at the bare metal level. Multi-processing was not active in my firmware. So I can focus here on core 0. Again, on this, if I do that, I will target these white things, which are memory cells, and my goal is really to target the AES encryption itself. So I will I would say, reduce a bit the area that I want to cover to only the logic that will be interesting to me. Okay, so I can select areas like this. If there are some countermeasures that are in place, like hardware countermeasures, for laser, you do have light detectors that can exist at the silicon level. I could try to identify where they are and put some exclusion areas as well in my scanning. Okay, so this is this way where I will specify on the green selected area all XY coordinates separated by 3 micrometer in my case will be covered in this area here. Okay, so here at the selection of the shape that will be covered, and then I need to handle the rest of the parameters. The XY step is the thing we just see before. The Z level, I can let it fixed or I can move it a bit. That could be interesting, especially on system on chip where you have multiple stages. So you will have multiple height basically inside the silicon. So maybe you would like to move the Zs and then refine with the OptiSpot. So this is why we, on this kind of device, accumulate the two options here to handle the focus for both optical and laser beam. The current level that we saw with the PDM HPP here, the pulse duration, the pulse delay, and the number of repetition to be sure that the events that we find is not purely random. So for all those parameters, I will not explain where those values come from. Basically comes from the experimentation. You will specify basically the ranges. So here for the OptiSpot, I will range from 40 to 110 by the step of 10 for each occurrences. The pulse duration, I will go from 15 nano to 230 nano, for instance. The delays, etc., etc. So here, for instance, for the pulse current, I will go from 35% to 71% by step of 5%. So those ranges will be taken by the different device that we have instantiated, so the OptiSpot, the PDM, and will be applied dynamically and automatically. I end up with this list of parameters, the repetition, the XYs, etc., and that will be automated in this process. So I would like to log everything for my experiment. So I go quickly on that one and start to define what needs to happen with my DUT. So here for my DUT, I will use NumPy, generate a set of key and the plane that I will use as a reference. I set this key. So here I have control of the device. I set this key and then I ask my DUT to encrypt and I can verify that the encryption is correct regarding the selected key and plane. So it will be fixed, of course, the goal being to obtain something that does not correspond to the expected ciphertext during the course of this experiment. So to verify that everything is working and I can communicate with my DUT, I simply call multiple encryption and do that with a repetition. So I have a small test loop that will only take the repetition here. Here, from this experiment, very simple, I do have the same 40 all the time. I'm not faulting yet. So we will do that for the next point. Again, the DUT will crash. So we'll need to reset it cleanly, basically. So I have a small function to do that. Again, not the most interesting thing here. And this is when I will start to define what needs to happen. So in my test function, I will try to encrypt the plane. And from this moment, according to the setup, how it is done, the trigger will be sent to the scope, or will be obtained by the scope. The scope will then send this trigger out to the delay generator. The delay generator will take into account the parameter I gave it and send back the trigger signal to the laser source, which will then shoot the laser beam on the device. Okay, so this is how it is interconnected. So as soon as I call an encryption, all this chain of execution will take place. So my point here, is simplified, of course, is if I find some outputs that are different from the expected one, here I pass, but this is basically what I will look for and try to obtain. So here, when I will launch the experiment, in this example, again, it's adapted. This one would take very, very long because it's clearly suboptimal here. What I will do when I do that, this XY stage will automatically go to each and every XY location that I have selected in this area with these steps separating those. As you can see here, I'm testing lots of different delays for the fault injection dynamically. And my laser is on, and I'm also going through a range of peak currents in this execution. So the OptiSpot will also change value from time to time according to the range I have selected. Okay, so this is how the experiment will take place. So it was this test loop here. And here, for instance, after less than 1 minute, I already have injected more than 3,000 laser pulses on the chip. So it can be quite fast. If the device is fast, that's great. However, as soon as it will start to crash, everything will be slower because we will need to restart. It will need to reboot. So this is why we try to minimize basically the area to cover, the time frame to cover, and also the failure like mute mechanism or simply crashes. But the real loop that actually was used for this experiment is below. I had to define several like Boolean options or counters. And I had also to handle different problems that are expected for this kind of experiments. I would need to define some conditions where to skip basically the experiment because I have too many mutes or too many crashes in this specific region. So what I do, I just skip lots of XY points. I go elsewhere. So I can do that automatically upon some conditions. So each time I finish a line, I can also like reset my device to be sure a non-catched fault will not mess with the rest of the experiment. So I can handle all these kind of things. And here, of course, I will just send my encryption, get the output, and try to get out of the output what is the behavior that we observe. Either the size of the output is not the expected one. If that's the case, I will try again with basically a switch case, trying to understand what happened, classify the behavior, and end up having my fault injection campaign. Okay, so here, as you can see in the exceptions, I can have timeout error, so I reset the DUT. I can have some mute mechanism. I can have synchronous abort from the CPU itself. I can have the U-boot, basically it restarted alone, or something that I don't know because I have not analyzed yet this kind of behavior. So I can classify all this. And during the course of the experiment, you can basically check at what are the outputs, how many were observed, what are the shape, and if you have something interesting for the fault injection, for the DFA, sorry. And also you will be able to get all the characteristics. So at which delay you start to have something, etc. At the end, you end up with this kind of cartography. So I'm closing that so it's bigger, where for the selected area, you will see lots of behavior. So you have faulties, you have presets, sometimes you have exploitable faulty, which is what I want to get. And those exploitable faulty, if you look here, are really concentrated to this location. And all this time I've spent with 3 micrometer step in this area were for nothing. So next time, which I did, I just focused on that and refined the parameter, and it was way faster. You could spend multiple weeks for the first time trying to locate the time, space, energy parameters. But once you have found it, reproducing the attack could be a matter of minutes or hours, to be more realistic. So it can be very powerful. And to get even more insight on this particular area, I have so this widget where I overlaid basically these outputs. You can see where it is active. I can just see what also are the behavior. I can just zoom into it and have the same view. So to those locations below, I have lots of different behavior, sometimes lots of unknown here, lots of unknown to those locations in particular, and to some location, lots of crashes. So it's really not great areas and not really easy to work with. Whereas here, in this part of the CPU core 0, I can see that I have lots of locations where I only have faulty ciphertexts. That could be potentially exploitable, so I need to filter out all the results. And if you analyze, basically for this case, why this area in particular, it matches the neon instructions that are used by the AES accelerated by the ARM v8 core. So it actually makes sense why this location provides so many faulty ciphertext. And from this, I will simply extract those ciphertext and perform my DFA. I will not go into the DFA process. We've seen that the last time, but basically this is how you would drive the fault injection experiments on such devices. So lots of challenge to overcome, but at the end, yeah, still works. Back to you, Oren.
Thank you, Lionel. So, just to wrap up, do you see my screen, by the way? Yeah. I would like to highlight our next activities. So we announced the new advanced hardware hacking training. If your company looking for training either for beginners in that field or advanced people, please contact us. There is a specific discount for companies until February that would like to book the training somewhere in the year. So yeah, this is one thing. About us, we are partner of eShard. We are the ARM training center. So we train all the silicon vendors around the world: Apple, Samsung, Marvell, Broadcom, NXP, etc. All the IPs, by the way. We are FPGA, Altera FPGA training partner, Cadence for verification, like System Verilog in UVM, and of course, hacking and defending for that. All of the trainings are hands-on, so it's not just theory, it's practical. And if you would like to have, you can contact us. Last thing, our next webinar that is going to be announced later and distributed to you is advanced hardware hacking modern techniques. This is going to, if you ask yourself what's going to be the agenda behind that, it's still not fully closed, but the idea is that we would like to discuss how to plan side channel attack and fault injection against highly secure devices, something that Lionel showed here in one example. We would like to discuss profile and non-profile attacks, so template attacks, high order attacks, like MIA, ANOVA, PCA, linear regression, and machine learning. And we will use for the demo the ES dynamic to show how complex attacks can be used. I hope that you enjoyed this webinar. Sorry for that it takes a little bit more than an hour. But yeah, we would like to give the community as much information as possible. So I hope you appreciate that. We appreciate your time, and we know that it's all in your schedule. It's not always easy to join webinars, so we try to bring added value information here. So I hope you enjoy that, you learned something new, and we wish you a great day, evening, morning, whatever you are, and hope to see you again on our next webinars and training. By the way, if you have any questions, you can still type them in the chat. We are still here for a few more minutes.